Okay, so, some short notes. It is possible to make small errors and have your networks still work. Many broken networks can still solve simple problems like OR and XOR, right? So, OR and XOR are not really good tests for a network because you actually can mess your network up quite a bit and it will still ultimately converge on OR and XOR, right? This is also because some errors end up introducing a constant offset to what the correct weight update should be. And that is mathematically equivalent to just having, I shouldn't use C, we'll say C2, to just having like some small offset to the learning rate, right? So some errors that are errors just show up as if you had slightly moved your learning rate, right? Those errors are, they're, they might be theoretically vexing. They are not like dramatic problems. The fact that a broken network can still converge on very simple problems, right? This suggests that we need to look for non-trivial tests for our networks, right? And we've even kind of reached the point, and we'll talk about this later, right? But even some simple data sets like MNIST are now effectively solved by sort of modern, large, deep networks, right? Again, to sort of talk about epsilons, right? We have already reached the point where you can kind of come within epsilon of perfect, or you can beat human performance, right, by a comfortable margin on MNIST. So even MNIST is not really a great test case anymore. But yeah, it's possible to make small errors and have your network still work, so be diligent, okay? I guess I should say, so I mentioned before that our network was doing a perfect job of mapping 0 to 0, right? That maybe isn't a good or impressive thing because it actually has to. Inputs of 0 with our basic layout must have an output of 0. Why is that? Well, let's talk about our 2x1 network, just so I don't have to do a lot of math, right? That has a 1x2 weight matrix. The input is a 2x1 column vector. If these are 0, if the inputs are 0, what do we get? Well, we have to get W1 times 0 plus W2 times 0, which, again, has to equal 0. What is tan h of 0? It is 0. So if we're using a tan h nonlinearity and a basic W times x input, then the output of our network for 0 must be 0, right? So again, it's not surprising that our network is learning to... What the heck just happened? Why did it minimize? Wow, that was surprising, right? So it's not surprising that our network is learning to perfectly map 0 to 0. It has to do that. It can't not, right? That's a problem. Well, the solution is a bias term. We're just adding a little offset, right? So, to get our pre-activation, right, our pre-activation goes from being y equals wx to being y equals wx plus b. So, what dimensions does b have to have? It has to have the height, right? So it has to match the output of this, right? So it has to match the output of wx, which means it has to have the same dimensions as the pre-input, which means it has to be the height of w by 1, right? So if w is a 1 by 2 and x is a 2 by 1, then the output of that is going to be a 1 by 1, and that's what B has to be to add to it, okay? So if we have a hidden layer of size j, right, then W has to have height j, and B has to be a j by 1, right? We good? So if you're curious, the term for Wx plus B is an affine transformation. This is a broad class of transformations from linear algebra. We don't need to know or understand that. It's just a little bit of trivia for the more mathematically inclined. With this, we maintain all of the expressive power we had before from this translation, and we gain the ability to shift our output, which is important if we want 0 to not map, so 0 input to not map to 0 output, right? We can move that sort of, we can move that point. So biases, which is what these are, so the derivative of the bias is just this thing, right? If we invoke the daemon calculus, again, a little Farnsworth, praise calculus. Farnsworth, glasses, kind of, whatever. So if we invoke calculus, we get this as the derivative for the biases. Remember that this was the derivative from the weights. It's the same thing, we're just not multiplying by the input to explode it into a matrix. That actually makes sense if you think about it, right? It's the same sort of, it's the same kind of error signal, if you will, but without the information from the input. Why should the information from the input not matter? Because the bias term does not depend on the input, right? The weight matrix is multiplied by the input, but the bias isn't. Excuse me. So, we also can exploit this. I'm not going to, that's left as an exercise for the reader, but since the update for the bias is part of, like the same math, is part of the update for the weights, we actually can exploit this to calculate our biases very, very efficiently, right? So here is, putting it all together, our forward pass and back pass for a biased network. Notice that I'm still going to draw the biased networks like this, right? I am not going to graphically represent the biases, okay? It is reasonable to initialize your biases to 0. We'll talk about why later, and in fact, TensorFlow will do this for us without asking, right? TensorFlow, by default, will have biases on and will initialize them to 0, which, perhaps unsurprisingly is the correct behavior, right? So now, notice my forward pass just has this plus B1 in here. Now, so again, I have not done this intelligently, right? Exploiting this, right, is going to be an exercise for the user. I'm just computing it explicitly twice. But I'm computing my weight update and then my bias update. Then I'm computing my backprop error. Then I'm doing my weight update and my bias update. Then I'm applying all of them. Just to be explicitly clear, right, the bias is still multiplied by the learning rate. Both the bias and the weight matrix are just parameters set inside theta, right? And stochastic gradient descent has the same update rule for all parameters in theta. Yep. So, biases are cheap, right? By cheap, I mean both computationally cheap and memory cheap. They have, in fact, the same computation and memory cost of just adding one more row to the matrix. So it is as if you had one more output, which is really cheap, right? Think about a very large, high output matrix adding, so if you have 300 outs, let's say, adding a 301st one is not very expensive, right? They often help, right? They very frequently improve the modeling capability of your network. They are sometimes essential, right? If you need 0 to go to not 0, you have to have biases, and they pretty much never hurt. I am aware of no problem for which adding a bias reduces modeling performance, and we wouldn't expect it to, right? Because a bias of 0, right? If biases get initted to 0, that's the same as not having them, right? So if they were going to hurt, just leaving them as 0, gradient descent wouldn't update them. Kind of butchered that sentence, right? But if we initialize them as 0 and not having biases would have been good, then gradient descent will just never make them non-zero. That's what I'm trying to get to. So basically always use them. In fact, they're default on in TensorFlow, and many other resources will just not even talk about the non-biased case, right? We started talking about the non-biased WX case. Some places don't. Some places just do it WX plus B right from the beginning, because you pretty much always should have your biases. They're cheap, they never hurt, they often help. So from here on out, pretty much always do biases. All right. So a trick that you'll sometimes see is people implementing biases by adding an extra unit to the input and an extra row, and always giving it the value 1. So an extra row on the weight matrix, or equivalently an extra input unit, and just always giving it the value 1. And a good exercise for the reader is to think about what that's going to be, right? Maybe think about what a bunch of that sum notation would end up looking like, and then see if you can formulate this, right? Adding an extra input to the matrix that always has that is always given input 1. Ugh. And then see if you can translate that to an equivalent statement like this, right? It works out the same mathematically, it's uglier notation, and we don't need to do that to ourselves because NumPy makes it very easy to just write WX plus B, right? We don't need to be memory tricky, we have NumPy to do all the hard work for us. Okay. And that is everything for this week. Next week we will start with TensorFlow. And again, since I'm recording this and posting this on a Friday like I'm supposed to, I should specify, whoopsie doodle, that, oh no, I'm getting ahead of myself. We have one more thing.